All right. So today we're going to continue with the multiple linear regression activity here. So as a reminder, we were working with this data set on the Great Lakes. Collected from this network of buoys around all the different Great Lakes, and they collect a lot of data. So we were looking at how we can use multiple linear regression to model some of the relationships in this data, particularly looking at how we can predict peak wave heights that these buoys measure using wind speed and temperature that are recorded by the buoys. Okay. And so we looked at, first we started with a review of simple linear regression, looking at just using wind speed as a predictor. And then we got to multiple linear regression where we were using temperature and wind speed. Okay. And we had just gotten to like the ANOVA table for multiple linear regression. Okay. I think we had talked about this last time, but I didn't write it in here. So what's the quickest way to calculate this? We call this like the standard error of the regression. And so it's equal to the square root of SSE over n minus k minus 1. But that value is already a little bit easier to get in the table than using SSE and n minus k over 1. If we were given the whole ANOVA table, I think I mentioned this last time. Does anybody know what this value underneath the square root is equal to? Someone remember? The numerator or the denominator, this is the degrees of freedom error. And then what's the whole thing underneath the square root there? MSE. So the quickest way is to calculate, and then we can just copy this equation. It was a little bit early, 8 something in the morning to be talking about ANOVA tables, but that's what we're here for, I guess. So, okay. Okay. And how can we interpret this in context? So according to the Stat2 textbook, which I trust, they indicate that this value right here this gives the typical size of a residual, or in other words, residual / prediction error. So it describes how much we expect our model to typically be off by for a given prediction. So very helpful because it quantifies how in a way, how well our model is doing. And lots of predictive models, not just linear regression. Like if you go into like machine learning or like data science, MSE is a widely popular metric just to describe how well a model is doing, because it describes how accurate the predictions are. Like I just finished up a predictive modeling like competition for the NCAA basketball tournament. And the criteria they used to determine who the winner was who had the smallest square root of the MSE for their predictions for the tournament. So yeah, widely used because it's a nice, simple, interpretable measure for how well your model does. Right. So that's one useful thing that's directly available from the ANOVA table. As a reminder, sort of putting it in context to like why we bother with the ANOVA table. I think, so it's nice that it sort of makes clear how some of these calculations come about. Like MSE, you can see the steps to get it. You calculate degrees of freedom error in SSE, because as a reminder, the formula for MSE, okay, MSE is equal to SSE divided by n minus k minus 1, right? And similarly, MS model is equal to SS model over k. Each of the MS's is equal to its corresponding SS over its degrees of freedom. Okay. And then this is the same for ANOVA as it was for ANOVA as well. If we had all these values, how could we calculate the F test statistic in the ANOVA table? I know it's been like many weeks, but
the MS model divided by MSE.
Yeah, perfect. MS model over MSE. So that's kind of why it's sort of like the people who made this table, it's like they work left to right with the calculations, with their end goal being the p-value is what they were after. But I feel like the ANOVA table is somewhat like an artifact of, or a result of people having to do things by hand before, and they like broke down the problem into smaller pieces. And it's just sort of like carried on, like people still report it as part of analyses, but it also has the nice property that like the square root of the MSE has this nice interpretable, this nice interpretation to it. What else is nice about it? I guess that's it. MSE is interpretable. Yeah. Yeah, that's kind of it. But oh, and the SS values. Yeah. The SS values are interpretable as well, just like we talked about in ANOVA. So if you have, and I put this in the guide document as well. Go to the bottom of the course schedule. That's always one spot to find the guide document. I think I added, it's a little small here. Yeah, I added the ANOVA table, and now it's actually nearly identical how you interpret the SS values as we did for ANOVA. Okay, so those are also interpretable. The square root of the MSE gives us the typical size of a residual, and then each of the SS values, so like SS total, the total variability in the response variable, SS model is how much variability in the response was explained by our model, and SSE is how much was not explained by the model. Okay. So that's a nice property. Yeah, here's the formal equations, which I will not ask you to calculate them by hand, but you'll just be given the ANOVA table. What might happen is you might have like one cell of the ANOVA tables missing, and you need to fill it in based on the equations that we know that relate the different parts of the ANOVA table. And like knowing that K is the number of predictors, N is the sample size. So you could be given like model output like this. Yeah, model output like this, and then given that in the sample size, we could fill in the whole degrees of freedom column, for example. Okay. So yeah, ANOVA table is useful in many ways. We were just talking about. The primary goal typically for it is to implement what's called an F test, which is equivalent to the F test for ANOVA, but now it has a slightly different interpretation for regression. So for the multiple linear regression model, the F test is testing if all the slopes, so not the intercept, just the slopes, if all the slopes are simultaneously equal to 0, versus an alternative of at least one slope being non-zero. And how we interpret that in words is that the null is that none of them are linearly related to y, none of the x's are. And then the alternative hypothesis is that at least one. Sounds familiar, right? Like it's similar to ANOVA, where it was like all the means are equal versus at least one pair of means was not equal. Okay. And again, yeah, the similarities arise because actually they're getting at the same exact problem. They're just reworked using different notation and thinking about the problem differently. But the theory underlying both tests are exactly the same, the ANOVA model and this multiple linear regression model. Okay, so looking at the ANOVA table for our two predictor model, where we were predicting wave height using temperature and wind speed. Okay, you can see the DF model is two predictors. The bottom one is n-1, degrees of freedom total is n-1, so that's how we knew there was 69 observations. And the SS columns. Okay. So lots of information here. Let's practice giving the hypotheses for the F test. So we can say like hypotheses are and then just like when we give the estimated model and the assumed regression model. This is like the most general form with k predictors, but we know how many predictors we have here, right? So we can get rid of this part since we have just 2 predictors. And not just like we can get rid of it, we should get rid of it to be clear about what we're testing. Okay. And then we want to give what these mean in context. This is important. So here we'll say our null hypothesis is that neither wind speed nor temperature. I guess we should probably add the units of measurement too. Neither of those are linearly related to the wave heights. And our alternative hypothesis is that at least one of wind speed and temperature are linearly related to the wave heights. Yeah. I think I showed you all this before, but it's nice in Google Docs if you ever want to insert a symbol like beta. It has this nice special characters feature now. You can go insert special characters and you can like draw the symbol. So like, let's say I wanted a mu. It knows, and then you can click it. I like beta. Ooh, it's really bad, but it still knew what I meant. Kind of nice. Okay. Any questions about those hypotheses? All right. Okay, so then giving our decision and interpretation in context. So the decisions, just the possible decisions are reject HO or fail to reject HO. Same old story in statistics. We're always doing these hypothesis tests where we're making some decision about the null hypothesis. So based on the ANOVA table up here, what's our decision and I guess why? Bless you. Yeah, reject HO, right? And what from the table told us that? Right, this last column. Yeah. So again, yeah, the tradition, just like with ANOVA and the t-tests, chi-square test, everything in statistics, everyone uses 0.05 pretty much all the time to compare for the p-value. So we'll say since the p-value is less than 0.05. Okay, so we should always give what the value of the p-value was from the table, and then say why, and then say what we're doing. And then interpreting that in context, this is kind of similar to ANOVA, where the initial f-test tells us a little bit, but it kind of leaves the results ambiguous. So we just say we have evidence that, and then it's like insert alternative hypothesis in words, right? That's how we always interpret the results for hypothesis tests. So we have evidence that we can literally copy like what we put for the alternative hypothesis before. And I guess we'll add at the 5% significance level. Although honestly, this p-value is so small that any significance level that people use, it would be statistically significant. And I guess I'll also add that I feel like in regression, it starts to get into this area of like regression is used a lot by like data scientists and statisticians, where statisticians are maybe, I feel like, more particular about procedures in statistics, and data scientists are a little more lax, maybe. So like, I feel like from a statistics perspective, someone would say like, never use the model, or generally shouldn't use the model if the p-value is above 0.05, but like data scientists might not be as concerned about that result and say like, if it's close, you know, that's fine. We can still use the model. So I guess what I'm saying is like, we use this arbitrary cutoff, but that doesn't mean the model's useless if the p-value is 0.08. You know, people would likely still use that model in full if that's the case, but just the convention in statistics is to treat this 0.05 cutoff as like some deterministic thing about whether we found a result or not, but that's oversimplifying things. So, okay, so just like ANOVA, this leaves the result a little ambiguous. We're just saying at least one of the predictors is related to the response. We're not saying if it's one or both, or which one, if it's only one. Okay, we don't know. So that's where, in one way, ANOVA, we would do what's called the post hoc procedure, right? So if you found a statistically significant f-test, you then conduct all the pairwise t-tests between the groups for one-way ANOVA. The analogous thing in multiple linear regression here is that we then, okay, so if we found at least one of the slopes differs from 0, we then proceed with doing a t-test for the individual slopes to see like, okay, which one is different from 0 since our f-test was significant. So SAS gives you this output. I made it general, but all these would be numbers in here, where it gives you the beta hats, their standard errors. And then to test if each beta is 0 or not, if the true beta is 0 or not, it involves a t-test. Each one of those has its own t-test, and each one has its own p-value. Okay. So, for example, to test if wind speed, which was x1, is linearly related to y, the wave heights, after accounting for temperature, since it's multiple linear regression, we interpret it that way. Here's our hypotheses, and then that's how we can describe HO. And so here's the general table for the individual tests of the betas. And then here's the table for this given data set with the numbers filled in. Okay. So yeah, again, with the statistics is all just a bunch of hypothesis tests always, where we're deciding if we reject the null or not. So now we have a new null. What's our decision regarding the test of wind speed here? We reject the null, yeah. So we reject HO. Oops. Since the right, and what was the p-value for this test of wind speed? Yeah, it's less than 0.0001. And that happened to be the same as the overall F test, but those are not. It's not like those are in general the same. That just happened to be. And SAS just, if it's really small, just always says less than 0.0001. So we reject HO, and what does that mean? So that means, and yeah, again, it's always with the hypothesis test, we say we have evidence that, and then it's like, alternative hypothesis in words, right? At the 5% significance level. This is how it is for like every single hypothesis test. So here, HA in words is how would we say the alternative hypothesis for this problem? Yeah, exactly. So that means speed in knots is linearly related to the wave heights in feet. And then very important to add after accounting for temperature. And this is almost there. But this is still leaving something a little ambiguous that we can be more specific about. So we're saying there's a linear relationship, but it's important to be specific about that relationship, right? Right, if it's positive or negative. So So here, yeah, so what can we say here? Is it positive or negative? Positive, right? Because what tells us that is just simply because this number in the estimate column is positive for wind speed. How do you word this nicely? We have evidence that wind speed, I guess maybe we'll word it as, has a positive linear relationship with the wave heights in feet. Yeah, we'll just word it that way. And we can go through the same test for temperature. So let's see. Let's start with just pasting this. So for the test of temperature, though, we failed to reject HO, right? Since the p-value 0.9603 is greater than. Whenever you have a not statistically significant result, we would say, like very generally, we would say, one way to say it is we have n, oops, and it's like, that's how we can do it for a result that's not statistically significant. Right? And then here in this context, that is HA in words is, we have insufficient evidence that temperature is linearly related to the wind speed, temperature in Fahrenheit. After accounting for wind speed. Oh, no, I'm sorry, not wind speed. It's wave height. Important to add this part in the interpretation because it very well could be the case that if you fit a simple linear regression between temperature and wave heights, you might find the p-value to be small. That's possible. So this is only saying like after we account for what the wind is, temperature is not telling us much about what the wave heights will look like. And so what does that mean for the model? This suggests that we should refit the model excluding temperature as a predictor. So this is one way in which we can, some people would call it like pruning the model, like trimming it down, or conducting model selection, deciding which predictors to keep in your model. Doing these individual t-tests is one way to do that. There's many other ways, but that's how we're going to cover it in this class. So. And you'll notice that there's a row for the intercept as well. Okay, so this is testing if the true intercept is equal to 0 or not. That's a t-test that you can do. And they talk about this in the book, in the Stat2 book. People don't really do that test very much. Just because simply you're not usually interested in the intercept. And it's sort of like a convention, I guess. Like you trim down the model by potentially removing predictors if they're not statistically significant. People don't really do the same thing. Well, not really. People don't do the same thing with the intercept term, which is a little bit contradictory, I guess, to be honest. But usually people just always keep the intercept in the model because you can fit a intercept-free model. But that's not done unless there's like a very special or specific reason why you should not have an intercept in the model. Like I'm on the Zoom meeting, so I should do it on the screen. For example, I'm like when I predict the basketball games, right? I maybe have like, I'm modeling like how much maybe I'm like modeling basketball games for any given team. And then I have like an intercept. This is so y is like how much team A will win by. Okay, this is like what I did for some of the basketball modeling. And then you have like x1 times its own slope, and then you have x2 times its own slope. Okay. And then maybe I have like x1 is team A's win percentage for the year, like what percent of games they've won. And then x2 is team B's win percentage, right? And then whichever team is like designated team A in each game is just random or arbitrary. In that case, like the intercept here is representing like how much team A would win by. Just on average, if the teams had the same exact win percentage. But we wouldn't expect if it's randomly determined which one's team A, which one's like the reference team, we wouldn't expect them to have a particular advantage over the other team if it's randomly decided. So like in that case, this is like one example where it would, I guess makes sense that you would want to exclude the intercept because it really should be 0 just by construction of the data set. But it's kind of a specific case, and very often it just makes sense just to always include the intercept and not worry about testing it. It's kind of a specific example, but nearly always, I think it's a safe bet to just include the intercept in the model, no matter what. That's commonly what people do. So we don't even talk about testing that, but it's something you might see. Okay. So we looked at this 2 predictor problem for multiple linear regression. Okay. Which was one of the simplest multiple linear regression models you could have. We had 2 quantitative predictors, which were completely separate from each other, 1 quantitative response variable. If you remember, for all our interpretations, we always keep saying whether or not there's a linear relationship between each x and y. Okay. Which honestly is quite a strict constraint on the relationship, right? Lots of things in real life are non-linear. You can have let's see. Like x and y like this. Okay. You can have something like this. Okay. That's like a relationship with x and y. Linear regression can't be directly used right away. So, out on that. Even just something as simply as like exponential growth, like this. Okay. That's nonlinear. So again, linear regression is not directly applicable. Okay. There's all kinds of, there's infinitely many ways we could draw a nonlinear relationship between x and y. But for a straight line, it needs to be something like this, right? And it could be negative as well. But the point being that just assuming that if there's a relationship between x and y, that it must be linear is not a safe assumption. It very well could be the case that it's non-linear. So like looking at the relationship between wind speed and wave heights, for example, I would say it's not super clear that this is a straight line relationship. Like, sure, straight line fits this pretty well, right? It's like, that's not bad. But maybe we'd have better predictions if we could fit it with like a curve like that. If we can have like a exponential growth here in the relationship, maybe our predictions would be more accurate. Okay. So fortunately, we can still actually get this like set of predictions or a predictive model that corresponds to this using simple linear regression, just with a little bit of extra work. Okay. And so one way to do that is to include functions of that predictor that has a nonlinear relationship as additional predictors in the model. And this is very commonly done. So for example, if wind speed is x1, we can include additional an additional predictor in the model, which we could call x2, but it's actually just equal to x1 squared. So now here's what you're actually using to model the response variable y. But notation-wise, and in terms of the theory and the optimization, that's the same as a two predictor linear regression model. But now it's what we'd call a quadratic regression model. So it allows us to model nonlinear relationships using the same process as before. So this is nice. And SAS actually recognizes when we do this. So here's like the SAS code for how we would do that. Again, it looks like a two predictor model. It's exactly like a two predictor model. But now here's the implied regression fit. So it has a curve through the data rather than just a straight, perfectly straight line. And note how this looks in the data is that I think it's helpful to think about. So originally for our data, oh, actually we have I think I had a preview of the data up above, maybe. Yeah, okay. So we've got wind speed here, right, is a variable. So to fit the linear regression model before, we have to have a variable that's our response, which has a bunch of numbers in it, and a variable that has a predictor in it, the predictor variable values. So if you think about this like squared term, what it's like equivalent to is that I'll just get rid of this, date column. It's equivalent to us like doing this, where we really tiny, but there's a 2 up there. Now it's squared. And then see if ChatGPT can help us out. Oh no. Thanks, ChatGPT. Okay. Okay. No. Not as easy. So like 50, 82, 57, 61. 50, 82, 57, 61. Okay, and so on. You get the point. So it's like we have an additional column where we literally square the values, and now we just treat this as if it was a new predictor in our model. And we assume a linear relationship between this squared term and y after accounting for the other predictors. Okay. And just by doing that, the predicted values, if you plot it by what just the wind speed is, okay, this is the implied set of predicted values. It follows this nonlinear relationship now. So it's kind of like a way to trick the regression model, even though it's constrained to straight line relationships. We can just use different powers of the predictors and get essentially any polynomial relationship like this in the data. So maybe it would be like a cubic relationship or like quartic to the fourth power, or like quintic to the fifth power. Okay. So when we fit this quadratic regression model, again, one way to decide like what's better, just the straight line fit or the quadratic fit now. So we can decide that or assess that by looking at the t-test for the quadratic term. Okay. And you always start with like the higher order term when you're trying to trim down a model like this. You don't start with just plain old wind speed. You start with the highest power term. Okay, for like sensibility reasons and interpretability. At least that's as far as statisticians are concerned. Data scientists might not do that way, but that's in statistics, that's what's done. So here, what do we think about including the quadratic term in the model? Does that seem like it's useful? Yeah, and why do we feel that way? Yeah, the p-value is bigger than 0.05. So the p-value is larger than 0.05, and it's like 0.0650. So we could just like remove a data point to make that p-value less than 0.05, right? And then get the result we wanted. No, that would be bad. That's what some people do. But no, if we're modeling wind speeds, right? Again, I think it's good to keep in context that the only reason 0.05 is used as the cutoff is because some British statistician in like the 50s thought that 1 in 20 times was not that often. And 1 in 20 times corresponds to 0.05. So, you know, we could let that dictate like what our final model is, or you could keep in mind, you know, the fact that that's somewhat arbitrary. So it depends on the context, right? Again, like when I'm predicting basketball games, if I see this p-value of 0.06 and I'm deciding what to keep in my model, like I would not hesitate to just keep all the terms in the model. With a p-value of 0.06, I'm saying that's good enough. It looks like it's helping out. But if you're running like a clinical trial where you're determining like health outcomes for people, often in like a setting like that, you kind of have to follow a very fixed set of procedural steps. And so you can't just decide after the fact that, oh, now, well, it was close, so we'll say it was good enough. You know, you would maybe have to stick to the rules in that case. But again, it's all about context. Yeah, here we're predicting wave heights. So it's not gonna like affect people's health or well-being directly. So I would say, you know, but since it is close, one could argue for keeping the quadratic term in the model. Some people use a p-value cutoff of regression as being 0.10 or 0.15 because of this. So there's less, I would say there's less of a consensus. Like it's still sort of like the default is 0.05, but in some textbooks, like I've seen, they do say like use 0.15 for deciding to keep terms in the model or not. So yeah, it's a bit of a gray area. So I guess to give a definitive answer for what we should do in this class, so let's say in this class, we will always stick to the 0.05 cutoff just to keep things simple. but note in real life that that's, yeah, arbitrary. So, and honestly, like what I would do in this situation too is like look at the plot, which is not an objective way to do it, and just like compare how does a straight line look versus that curved line. Like which one looks like it's doing better to capture the trend in the points. Okay. I mean, the quadratic model maybe looks a little better, but honestly, they are pretty similar. So I think it wouldn't matter too much either way. Right. Okay. And then I don't think I have any questions. I don't have any questions about predicted values here, but note that this is like a good example of where you would want to be careful about extrapolation for predicted values. So like, let's say we're using our model to predict how tall the waves would be for a day. And it's a crazy windy day, like maybe like 40-mile-an-hour winds. Okay. What this model would tell us is that if you just used the predicted values for it, it's going to continue with this trend like this, right? Okay. And so you might get at like 40, at like 40, you might you might get like a predicted value of like 10 or 11 feet for the waves. There's very likely been 40-mile-an-hour winds on the Great Lakes. Is it likely that corresponds to there being like 11-foot waves? Probably not, right? So it seems likely, I mean, I'm not an expert on how waves work in the Great Lakes and things, but it seems likely that at some point in the relationship, it probably levels off where it maybe keeps getting windier, but the waves can only get so high, probably. We don't know where that point would be. And also we don't know if that's true or not. Like, I guess it might keep going up. It might like change how fast it's going up, the rate at which it's going up, or it might go up even faster. We don't know. The concise answer is we don't know. So all we can make predictions for is in this range of observed values. So always be skeptical or cautious about making predictions and making sure that it's not extrapolation. It's a very common misuse of regression models where people like to give some like crazy prediction, like, oh, if this trend continues, we're going to see this catastrophic event. And they often are doing that with like extrapolation because you can find some really extreme, predictions if you are predicting outside the scope of your data set, right? But always got to be skeptical or aware of that. Or like also here, there's some, I guess if you continued long enough, it looks like you could get negative predictions, but we know that's not possible, right? We went to the other side, to the left side. So because of extrapolation in part. All right, so in addition to testing individual predictors like that using p-values, we can also assess how well our model is fitting the data by using the R-squared value, which sometimes like the book called it, the Stat2 book called it the coefficient of multiple determination. But I think nearly like very often this is just referred to as R squared. Like people will say, what's the R squared of the model? The R squared can be interpreted as the proportion of variability in the response that is explained by our regression model. So for example, if you calculate R squared from the ANOVA table like this, and it's 0.75, so R squared will always be between 0 and 1. If you get 0.75, and for a two predictor model, we can interpret that as roughly 75% of the variability in Y is explained by X1 and X2. Okay. So that's another use of the ANOVA table. It tells us, it can give us the R squared value. Okay. And the reason it's denoted R squared is because it's actually a correlation coefficient that is squared. So specifically for simple linear regression, R squared is equal to the correlation between X and Y squared. But then generally, because multiple linear regression, you have several predictors, but it's actually equal to the correlation between the predicted values that you get, the Y hats, and the observed Ys themselves, and that correlation squared. Okay. So keeping that in mind, if we had like, okay, let's say this was our plot, and then we had X and we had Y. Okay. We got the straight line relationship. What if all of our data points were like this? Okay, they fell exactly on our line of best fit. What would the R squared be for this model here? It would be 1, right? The correlation between the predicted values, which are all on the straight line, and the actual Y values, which are given by the height of the points here. Those are perfectly correlated in like this example. So the R squared is going to be 1. And then if R squared is 0, that would correspond to your line of best fit having like no slope. The slope would be 0, and the line would be perfectly flat. That would tell us that the R squared is going to be 0. Okay. Any questions about that? Might be a good exam question. Okay, so let's maybe before we get to overfitting here, let's see what like the R squared was for the even though it's not asked for in a bullet here. Let's see what R squared was. For the model predicting wave height using wind speed and temperature. Okay, let's see what the R squared value was. Oops. Okay, so let's grab SS model and SS total from the ANOVA table. And then, okay, so here was the ANOVA table for the two predictor model. So we have that SS model. Was equal to what's our SS model value here? Right, yeah, the 119, this number here, 0.7884. Okay, and then SSE, or no, SS total is 266.2782. And I'll write them down here. So SS model we had. Oops. SS total should always be bigger than your SS model. Okay, we're not going to use this part of the equation. We're just using the first part. And if you round to 3 decimal places, you should get that. And so how could we interpret that here? So we can say, and then instead of 75%, we would say 45%. 45% of the variability in wind or wave heights. It's explained by so another good use of the ANOVA table. We can get the R squared value and then interpret it for our model. So in general, a higher R squared is typically better for a model. But note that it's nearly certain that anytime you add a predictor to the model, it will increase your R squared value. That doesn't mean it's good to add that predictor into the model. Okay. because we want to be careful of what's called overfitting in regression. So here's an example. So we added like an x squared term to the model to get like a curved prediction set of predictions. You could add an x cubed term and x to the fourth term as well. I think this is like x to the seventh up through that. And what happens is you get a, like some people call it a wigglier function. Like it gets wigglier and wigglier. And eventually, if you don't have too many data points, what happens is if you add enough terms of x, higher order terms, you will perfectly fit the data. And so your R squared is 1. And all your predictions are perfect, right? Which on the surface maybe seems like, great, yeah, we're doing a good job then. We have a really good model. But like, what's the problem with using this model versus like, here's just the linear regression with just x as a predictor in the blue line. Yeah.
You add like any other point, that line is not good.
Exactly. Like you add one other point, it'd probably be like here. It's going to do really poorly because it's probably going to end up being something like this. I mean, not certainly, but if you did this and then you look at the residual value for your predictions now, really bad compared to the straight line model, right? So this is where R squared can sort of lead you astray if you're not careful. It will always, it's like a greedy metric, they would call it. It wants more and more predictors always in the model. And this is an easy trap to fall into because, I mean, this is an extreme example where it looks very clear like, oh, this would do poor with fitting new values. But sometimes it's not super obvious. Like in the case with the quadratic fit, it could have been that we were overfitting slightly by using that quadratic term versus the linear, just the straight line. But it's not super clear unless we had more data to really evaluate that. So how can we decide like how wiggly is too wiggly for the function? How many predictors is too many predictors in our model? Okay, and so people have addressed this in many different ways. One of the ways that we're just going to use in this class is the adjusted R squared value. The adjusted R squared value is similar to the regular R squared value, except it penalizes for how many predictors you have in the model. So if you start just throwing in a bunch of predictors and they don't increase R squared a huge amount, this can actually start to go down. The adjusted R squared will start to go down, indicating that it's a worse model fit. Okay. So this will help us pick what we'd call a simpler model, meaning less predictors, that still does a good job. I forget, it's like oh, maybe ChatGPT knows. I think it's Occam's razor. Occam's razor, yeah. Okay, so like people, I think in economics and other terms like this, okay, yeah, ChatGPT is going on explaining all about Occam's razor. So this idea that you want a simpler model so that you don't overfit is like a principle in general, you know, like if you're trying to predict the weather today and it's like, I saw like this many clouds and the sky was this hue of blue and the humidity was this, like at some point using some information is good, but if you take into account too much, like, well, I woke up at 9 a.m. rather than 9:05. So I'm going to include that in my, information deciding what the weather is today. If you include too much information at some point, you're going to start to make bad predictions or guesses about the world. Just that idea is, yeah, someone described it a long time ago. Okay, so we'll finish up this activity next time. But yeah, have a good weekend.